Okay, welcome back everyone to the deep dive. We're here again to unpack the latest breakthroughs in artificial intelligence and machine learning. And today we're really plunging into, I think, one of the most exciting, but also, frankly, one of the most elusive frontiers in AI right now. That's the quest for, well, true abstract reasoning. This isn't just, about building smarter algorithms in the usual sense. It's really about pushing AI beyond that kind of rote pattern recognition, beyond statistical interpolation, towards something that feels a lot more like genuine intelligence. And right at the heart of that quest is this huge challenge of generalization. How can an AI system learn a really complex concept from maybe just a handful of examples, and then critically apply that understanding flawlessly to completely different scenarios, things it's never ever seen before? That's the monumental challenge, isn't it, facing AI today? And that's precisely what we're going to try and dissect here. We're diving into a brand new research paper, literally hot off the press today, August 13th, 2025. And it shines this fascinating light on how, well, what seems like a really small architectural tweak inside a neural network can lead to these surprisingly massive leaps in performance. And this really shows up when these systems face those critical, out of distribution challenges, problems that look fundamentally different from anything they saw during training.
Yeah, exactly. And our mission for this deep dive is really to pull back the curtain on the technical specifics and also the implications of two closely related network architectures. These are recurrent convolutional networks. We're talking about DARC first. That stands for depth-aware recurrent convolution. And then its sort of enhanced cousin, DAMP, which is the depth-aware multi-layer perceptron. We'll dig into the details, explore what makes DAMP so effective, and importantly, how these findings are pushing the boundaries of what we thought was possible in things like neural program synthesis and generalized AI. And as always, our focus is going to be squarely on the technical side, the architecture, the methodology, the performance numbers. We'll stick to that technical landscape. We'll avoid getting into the broader societal or ethical questions for this discussion. And just a quick reminder for those of you wanting to stay updated on the latest AI and ML papers, you can always visit our webpage, neuralintel.org, and check us out on YouTube as well.
Okay, great. Let's get into it. So let's start by really setting the stage for this core problem. The Abstraction and Reasoning Corpus ARC challenge was introduced by Francois Chalet back in 2019, and it really felt like a paradigm shift, didn't it? In terms of what we expect from intelligence systems, it's just fundamentally profoundly different from most of the deep learning benchmarks we've kind of gotten used to over the years. Normally, when we train a deep learning model, we feed it this colossal data set, millions, sometimes billions of examples. And the model's main job is basically to interpolate, right? To find patterns within that training data, connect the dots between things it's already seen. Think of it like teaching a kid to recognize a specific dog breed by showing them thousands and thousands of pictures of that breed. They get incredibly good at spotting that dog, even in new poses or different lighting, but only as long as it falls within the spectrum of variations they've already seen.
Right. It's still fundamentally pattern matching within the known distribution.
Exactly. But ARC, it demands something way more sophisticated. It just completely flips that script. Instead of interpolating within this huge predefined data set, ARC tasks demand that the AI discovers and then applies abstract rules, and it has to do this from just a few examples, like 2, 3, maybe 4 demonstrations. That's it.
Tiny amounts of data.
Tiny. It's more like showing that same kid, just 2 or 3 examples of a totally new kind of logical puzzle, maybe a sequence of colored blocks that transforms in a specific way. And then, with no more hints, no massive data set, you expect them to solve completely novel, much more complex versions of that puzzle, based purely on figuring out the underlying logic, not just recognizing visual similarities or interpolating pixels. This is about real generalization, true rule extraction. It's not memorization or superficial pattern matching. It's a leap, isn't it? From recognizing what is to understanding why something changes the way it does.
Absolutely. And understanding why this distinction is so critical for AI's progress is, well, it's key. Success in ARC isn't just about getting a high score on some niche benchmark. It points directly towards capabilities that are vital for what's called neural program synthesis. Now, this isn't necessarily about writing Python code in the traditional sense, though sometimes it is. It's more about where neural networks learn to generate these executable programs or perform systematic rule-based transformations on data. Imagine an AI that doesn't just classify an image, but can, say, identify a corrupted part of an image and then apply a learned logical rule to repair it. It's effectively programming itself to fix the problem based on understanding the rule. That requires a much deeper kind of understanding.
A generative capability based on rules, not just pixels.
Precisely. And what's also fascinating about ARC is how it inherently demands that models handle variable-sized inputs. The grids, the puzzles, they can be different heights, different widths, and the transformations, the rules, need to apply regardless of those input dimensions. This, combined with that need for strong generalization, extends way beyond ARC itself. These are fundamental properties needed for so many real-world vision and reasoning tasks where data isn't always neat and tidy, not always in fixed dimensions. Think about robotics, where objects are different sizes, or scientific discovery, where patterns might show up across varying scales. True understanding in those contexts means applying principles to new varied situations, not just re-recognizing familiar patterns. It's really about getting from the what to the how, and ultimately the why.
Okay, so given this huge challenge, moving beyond just interpolation to true abstraction, where are researchers seeing the most promising paths forward? Well, some recent work has strongly suggested that recurrent convolutional networks are a really compelling direction for achieving this kind of deep generalization. For instance, Schwarzschild and colleagues back in 2021, they demonstrated something pretty impressive. These architectures could successfully scale their performance from smaller, say, 9 by 9 mazes to significantly larger 13 by 13 ones. And they did this without needing retraining or big reconfigurations. That's a direct example of spatial generalization.
Yeah, that's a neat result.
And even more interestingly, they saw performance gains on complex chess puzzles just by letting the network do deeper test time iteration, basically letting it think longer, process the input more times before giving an answer.
More computation at test time helps.
Right. It's like giving the AI more internal steps, more cycles of refinement to really process and understand the problem before settling on a solution. This idea of iterative refinement feels powerful.
It really does. And if we connect this to the broader AI landscape, we're seeing strikingly similar findings popping up in other sophisticated architectures too, especially ones with adaptive depth mechanisms, like transformers, Fan, and others. Just this year, 2024, they showed impressive generalization with these kinds of models on abstract computational tasks, things like binary summation and multiplication, which are surprisingly hard for standard networks. And this really highlights, I think, a core cross-architectural insight. Any mechanism that lets a neural network dynamically adapt its computational depth or its information flow, essentially deciding how much processing is needed for a given input or a certain complexity, that seems absolutely key to learning more robust and generalizable patterns.
So it's not just about being deep, but about being adaptively deep.
Exactly. It's about flexibility and computational efficiency. Applying more thought or more iterative processing when a task really demands it, rather than having this fixed, rigid, one-size-fits-all computational path. This adaptive capability, it's a hallmark of intelligent systems, whether they're biological or artificial. It suggests that a fixed depth network, even a really, really deep one, might just be inherently limited in its ability to generalize across different levels of problem complexity.
So with that context, let's really peel back the layers and dive into the architectures themselves, starting with DARC, the depth-aware recurrent convolution network. This is the foundation, right? The baseline model where the story begins. At its core, DARC is actually quite elegantly simple, but still surprisingly powerful. It starts with a pretty straightforward linear embedding layer. You can imagine taking your input grid, which might be pixels, maybe numerical features, and transforming it into this richer, higher dimensional representation. Kind of like turning a simple sketch into a detailed, multi-layered blueprint.
Setting the stage for processing.
Exactly. Then, after this initial embedding, the real cleverness of DARC comes in with what the paper calls a looped convolution. Think about a standard convolutional block, great at finding local patterns, edges, corners in an image. Now, instead of just applying that block once, like in a standard feed-forward network, it's applied repeatedly, in a loop.
Okay, so it's recurrent.
Right. And with each loop, each iteration of this recurrent block, the network iteratively refines its understanding of the input grid. It does this by adding to something called a residual stream. Picture this residual stream like a constantly updating mental canvas or maybe a running tally. Each pass through the looped convolution doesn't start over. It builds upon the accumulated insights and transformations from the previous passes.
Adding information incrementally.
Yeah, like a sculptor who with each pass adds more detail, refines the form, never erasing what was there before, but always enhancing it. This constant refinement helps ensure that earlier, maybe simpler details aren't lost, but are consistently enriched and integrated into a more complete, nuanced picture. This iterative processing is what gives it that depth-aware quality.
And a really crucial aspect here, the thing that gives DARC its name, is precisely that depth-aware feature. It's vital to its adaptive nature. This recurrent convolutional block you just described, it isn't repeated a fixed number of times.
Mm.
Instead, the number of repetitions, let's call it n, is dynamically determined by the input grid size itself.
Okay, so it adapts to the input
Oh,
size.
exactly. Specifically, n is calculated as 2 times the maximum of the input grid's height or width. So n equals 2 times max, height, width. What this means practically is that larger input grids, which intuitively have more information and probably need more computational effort to process thoroughly, they automatically get more recurrent iterations. This automatically adapts the network's computational depth to the complexity and the scale of the input, makes it incredibly flexible.
That makes sense. More complex input, more processing steps.
Right. And then finally, at the very last iteration of this dynamic loop, that highly refined residual stream gets passed through the transpose of the initial embedding layer's weight matrix. This produces the final output grid. Now, this whole architecture inherently gives you several big benefits that make it pretty well suited for generalization tasks like ARC. First, it naturally handles variable input grid sizes without needing complex resizing or preprocessing. That's a huge plus for real-world data where things aren't always uniform. Second, it offers maybe degree of interpretability precisely because of that residual stream. You could, in theory, look at how the model builds up its understanding over time, see the intermediate stages of its thinking.
See how the representation evolves.
Exactly. And as the paper shows, DARC retains expressive functionality even at very small scales, demonstrating its versatility and robustness across different problem sizes. It's a solid foundation.
Okay, so DARC, as you've laid it out, sounds pretty innovative, handles variable sizes, iterative refinement, some interpretability, seems powerful on its own. But here's where the story gets really interesting. Enter DAMP, the depth-aware multilayer perceptron. DAMP is introduced as a direct variant of DARC, so it builds right on that foundation. And the architectural difference is, well, it's singular, but surprisingly incredibly impactful. DAMP simply adds a multilayer perceptron, an MLP, right after the depth-aware convolution within that recurrent loop.
Just one MLP block.
Just one. It's a shockingly small addition when you think about the dramatic impact it has on performance, which we'll get to. You could almost miss it looking at the diagram.
Yeah, it's subtle but crucial. And it's worth digging into the technical details of this MLP because it's not just any MLP. It processes the output of that recurrent convolution, but not spatially like the convolution does. It works channel-wise. So imagine your data grid isn't just one layer of information. It has multiple channels stacked up like RGB channels in color images, or the many feature maps a neural net develops.
Okay, so operating across the features for each location.
Exactly. This MLP operates on these channels independently for each pixel location, allowing for really rich interactions between the different channels of information at that spot. It's basically learning how to combine and transform these different feature maps effectively. And furthermore, it uses what's known as GLU gating. GLU stands for Gaussian Error Linear Unit. It's a type of activation function established by Shazier back in 2020. Think of it like a sophisticated soft switch. It decides how much of a signal gets through based on its strength and characteristics. This gating mechanism adds another layer of nonlinearity and expressivity. It lets the network learn more complex, nuanced relationships between different pieces of information that just summing them up wouldn't capture.
So it's a channel-wise MLP with this special GLU gating. Why is that seemingly small addition so significant then?
Well, the paper argues that it allows for rich expressivity in how the model can mix that channel information. You contrast this with DARC's simpler linear combination and thresholding within its residual updates, which offers less flexibility in how information across channels can interact. The theoretical implication here is pretty profound. While, sure, a sufficiently wide DARC could, in theory, approximate the function of this MLP through its convolutions and recurrent structure, the MLP potentially offers a more efficient and effective way to learn complex channel interactions.
More efficient, okay.
Yeah. And this is where it gets really interesting, because, as the paper itself points out, the 3x3 convolutions used in DARC already mix channels non-linearly.
They do.
Right, convolutions do that. They do. Yet the outsized impact of adding this single extra MLP is surprisingly powerful. This suggests it's not just about adding more computation or more nonlinearity in a kind of brute force way. Instead, the MLP seems to provide a fundamentally more efficient or maybe structurally better way for the network to integrate and process these channel features, leading to more robust and generalizable knowledge.
So maybe it's learning a different kind of channel interaction, more abstract.
That's a good way to put it.
Perhaps it's learning a more global, abstract feature combination across channels rather than just local spatial patterns combined with the channel mixing inherent in convolutions. It really seems to be about the quality and the location of this nonlinear mixing, not just the quantity.
Okay, so to really put dark and damp head-to-head and properly test their generalization chops, the researchers needed the right proving ground. They turned to a specific benchmark, the RCN dataset, introduced by Hodel in 2024. Now, you might ask why RCN? Why not the original IRC dataset? The key thing here, the reason it's so useful, lies deep in its design. RCN isn't just a static collection of puzzles, it's procedurally generated. What that means is for each of the 400 original ARC training tasks, RCN gives you a generator function.
A recipe for making tasks.
Exactly. Imagine having an algorithm or a recipe that can create an infinite variety of puzzles all based on the same core logical rule instead of just having a fixed set of examples. This procedural generation, it's a total game changer for testing generalization seriously.
Yeah, absolutely critical. And what's particularly crucial is that each of these generator functions has this configurable difficulty range. It's represented by all in U values, both between 0 and 1. This feature is absolutely central to its utility for evaluating true out-of-distribution generalization. It lets researchers train their models on tasks of a lower difficulty, say, examples generated with difficulty between zero point 0.3 and zero point 0.5.
Okay, train on the easier stuff.
Right. And then here's the key part. They can systematically evaluate out-of-distribution, or O, generalization, by testing the same models on higher difficulty tasks, like those generated with difficulty between 0.55 and zero point 0.8. This systematic approach lets them assess precisely how well the models generalize to more complex, totally unseen scenarios that demand a deeper grasp of the abstract rules. And they can do this across a wide variety of transformations. For this specific study, the researchers carefully picked 185 re-ARC tasks that met two main criteria. First, they had to preserve the grid size input, and output grids have the same dimensions. That simplifies things a bit architecturally.
Keeps the input-output shape consistent.
Right. And second, they had to generate quickly. More than 200 tasks per second on a single M3 Max CPU core, they report. This efficiency was vital for running the huge number of experiments needed for a robust evaluation.
Now, one of the real strengths of this research, something that really boosts the credibility of the findings, is the super meticulous setup they used. They were really careful to ensure a fair, direct comparison between dark and damp. They used two model instances. Dark was set up with 87.91K parameters, and damp had 87.55K parameters. Notice how incredibly close those numbers are.
Practically identical parameter counts.
Exactly. This parameter-matched approach is absolutely crucial. It means any performance difference they saw between the two models really isolates the architectural difference, that single MLP, rather than just being because one model had more capacity or more computational horsepower than the other.
Yeah, it removes a major confounding variable. It's like a well-controlled experiment.
For sure, and it makes the results much more compelling.
And digging a bit deeper into their method, the training process itself was also really rigorous, which further strengthens the results. Both models, dark and damp, were randomly initialized from scratch for every single task they learned.
Okay, fresh start for each task.
Fresh start every time. And here's a key detail. For each task, they used a different random feed for that initialization. Now, this isn't just a minor thing. It actively reinforces that the models aren't just getting lucky with some initial configuration or relying on one specific training run to get good results.
Shows the learning is robust.
Right. It demonstrates repeatable, robust learning. In terms of training volume, each model was trained for 2048 batches, and each batch had 16 examples. That totals 32,768 examples per task. And importantly, all these examples were consistently sampled from that lower difficulty range of REARs, between 0.3 and 0.5.
Sticking to the defined training difficulty.
It's exactly. For optimization, they chose the Nuon optimizer, which is known to perform well in certain contexts. They used a learning rate of 0.01, a short warm-up phase of 16 steps, and then a cosine decay schedule to gradually lower the learning rate way down to 10.7 by the end. And the loss function, pretty standard for these grid tasks, was cross-entropy loss. It measures the difference between the model's predicted output grid and the actual target grid, guiding the model to learn the right transformations pixel by pixel.
Now, to help us really get a feel for what difficulty actually means in REARs, the paper gives this fantastic visual example using task 49380C2. Let's try and picture this. Imagine a simple grid at difficulty 0.3. Maybe you see a small orange block and a yellow line as input. The output might be, say, Two yellow lines with that orange block now sitting neatly between them. It's a clear rule, maybe something like mirror the line and center the block. Simple enough.
Okay, a basic transformation.
Right. But now, here's where that difficulty scale kicks in. As you incrementally increase the difficulty, maybe to 0.40, the input grid might suddenly shift to all green colors, and the shapes might not just move, but also deform a bit, or scale slightly. By 0.50, maybe the colors are totally different again, and the transformation needed could be more intricate, multiple objects, their relative positions, complex relationships.
The visual appearance changes a lot.
Dramatically. Then you hit that out-of-distribution range, starting at 0.55, climbing up through 0.68, all the way to 0.80. At these higher difficulties, the input and output grids look very different from the low difficulty ones. The transformations become increasingly complex, multi-step, non-trivial.
So the underlying rule is the same, but manifesting in much harder ways.
Exactly. The abstract rule hasn't changed, but it's applied to scenarios that are visually, structurally, and logically much, much harder to figure out. This really pushes the model's ability to abstract the core logic to its absolute limit, rather than just recognizing superficial similarities. It's like asking someone to solve, I don't know, a simple algebraic equation, then giving them the same equation but with totally different numbers, maybe even different symbols, but the underlying math operations are identical. Can they still see the pattern?
That's a good analogy.
Yeah.
And it's crucial to stress a really important point about these grids used for evaluation, which the paper makes very clear. All the grids used for calculating both the in-distribution ID and the out-of-distribution accuracies were never seen by the model during training. Never.
Completely novel test data.
Absolutely fundamental for a true, unbiased test of generalization. These evaluation grids were sampled fresh from the generator function after training was done. They're genuinely new instances of the tasks. This means the model isn't just recalling patterns it saw before or interpolating within familiar territory. It's being presented with genuinely novel applications of the abstract rules it was supposed to have learned. And this rigorous methodology is precisely what lets the researchers confidently claim they're measuring true generalization, not just assessing memorization or how well it interpolates within the training set.
Right. It's the difference between a student acing a test with problems identical to their homework versus acing a test where they have to apply the principles they learned to totally new situations.
Exactly that difference.
All right, so the setup was meticulous, the benchmark designed for generalization. Let's dive into the results now because they really are compelling and highlight this surprising edge that DAMP has. For the evaluation, they sampled difficulty values in these precise 0.05 increments across both the ID and ODE ranges. At each of these difficulty points for each task, they generated 64 distinct grid instances using the ReArc generator, and each one was scored by exact match.
Which is a very strict metric.
Super strict. It means the model's output had to be pixel perfect, identical in every single detail to the target output grid. If even one pixel was wrong, the score for that instance was 0. Kaput.
No partial credit.
None at all. These 64 exact match scores were then averaged to get a difficulty level accuracy for that specific task at that specific difficulty. Then, the overall test accuracy for a particular task was the mean of these accuracies across all the sampled difficulty values for that task.
Okay, averaging across difficulties for each task.
Right. And this whole painstaking process was repeated for all 185 benchmark tasks they selected. The grand overall test accuracy they report is the mean of those per-task accuracies. Gives you a comprehensive picture.
Makes sense. And just to reiterate those specific ranges, because they're vital for understanding the results, test accuracy, ID, for in-distribution, covers the ReRRC difficulty range 0.3 to 0.5. That's the exact same difficulty range the models were trained on. So it measures performance in familiar territory.
Home turf, basically.
Exactly.
Oh.
Conversely, test accuracy, OAD, for out-of-distribution corresponds to the ReRRC difficulty range 0.55 to 0.8. This is the true out-of-distribution zone, unseen, higher difficulty tasks that really push the model's generalization abilities.
Yeah.
As we saw with that task 4938 Fiera's C2 example, the difference between the training distribution ID and these O testing distributions can be really dramatic for some tasks. It turns what looks like a simple rule into a complex puzzle.
So the ODE performance is the real stress test for abstract reasoning here.
Absolutely. It's not just a pattern interpolation anymore.
Okay, now for the headline numbers. And this is where DAMP really shines. The paper states quite clearly that the most striking performance differences were found when they looked at the median accuracy. For the in-distribution tasks, the familiar ones, DAMP achieved a median accuracy of, wow, 92.19%, pretty high.
Very strong performance.
DARC, its simpler baseline sibling, was respectable too at 78.75%. So even on the easier stuff, there's already a significant gap favoring DAMP.
A noticeable difference, yeah.
But here's where it gets truly astonishing. This is really the core finding, I think. For those challenging out-of-distribution tasks, DARC's median accuracy just plummeted, down to only 2.34%.
Wow. Almost complete failure on the median.
Basically, yeah. It means DARC could barely solve any of the harder, unseen versions of the tasks it was trained on, at least for the median task. In stark contrast, DAMP achieved a remarkable 14.58% median accuracy on ODE tasks.
Okay, still not super high in absolute terms, but compared to 2.34%, that's a huge relative difference.
Huge. It's not just a small incremental improvement. It's a profound standout difference in capability. It really suggests DAMP has this ability to retain its understanding and generalize much more effectively when faced with fundamentally new levels of complexity, with unseen data.
This is where that single architectural tweak, that MLP, really seems to prove its worth when the reasoning gets tough. It suggests it unlocks a different quality of learned representation, one that's far more robust when things get weird and novel.
Yeah, it's surviving the generalization cliff much better. Beyond those really striking median figures, the consistent outperformance of DAMP is also clear when you look at the mean accuracies. These give you a sense of the overall average performance across all the tasks. DAMP consistently outperformed DARC across both ID and, crucially, ODE scenarios. For in-distribution, DAMP's mean accuracy was 60.21% compared to DARC's 54.77%.
Okay, a solid lead there too.
And for the tougher out-of-distribution tasks, DAMP achieved 38.98% mean accuracy versus DARC's 31.08%.
Right, so roughly an 8% absolute improvement in mean ODE accuracy. That's substantial.
Definitely not minor fluctuations or statistical noise. It shows a clear, consistent advantage for DAMP, meaning it's reliably solving more problems correctly on average.
And it's important to stress the statistical significance behind these mean differences. The paper is rigorous here. They state the mean accuracy difference is statistically significant, with a p-value less than 0.0001 for both ID and ODE tasks.
Very unlikely to be chance.
Extremely unlikely. Furthermore, the 95% confidence intervals they calculate for the mean difference between DAMP and DARC, they consistently exclude 0 for both ID and ODE. That's a very strong statistical indicator that these performance gains are real, a genuine effect of DAMP's architecture. And if you connect this to practical terms, look at the win-velocity analysis they did. It further underlines DAMP's edge. DAMP outright outperformed DARC in 43.2% of the in-distribution tasks. But even more tellingly, it outperformed DARC in an even higher percentage, 48.1% of the out-of-distribution tasks.
So it wins more often, especially when things get harder?
Exactly. It's not just about small average gains. It's about DAMP solving a significantly larger chunk of tasks entirely correctly compared to DARC, particularly when the difficulty and novelty ramp up. More perfect solutions, more often on the toughest problems. That feels meaningful.
Now, while these results for DAMP are definitely impressive, a significant step forward, it's also important we acknowledge the limitations. The paper is refreshingly honest about this. Both methods, DARC and DAMP, still completely failed on a noticeable chunk of tasks. We're talking 22.7% of ID tasks and a pretty substantial 38.4% of ODE tasks.
Yeah, nearly 40% failure on the hard stuff.
Right. So for almost a quarter of the easy tasks and over a third of the hard ones, neither model could find any solution at all. And furthermore, the mean ODE accuracy for both, even for the improved DAMP, is still below 40%. This tells us that while progress is being made, absolutely, there's still a long way to go before we have anything close to a general, robust solution for these kinds of abstract reasoning challenges.
It's definitely not a silver bullet for RCGI yet. It's a step, a potentially important one, but still a step.
A powerful step, but yeah, not the final destination.
And this actually brings up a critical point about some of the statistical findings in the paper that might seem a bit confusing at first glance. While Cohen's D-values, which measure effect size, showed a small effect for ID, 0.281, and a medium effect for ODE, 0.481, the Cliff-SO values, another effect size measure, surprisingly suggested negligible practical significance. They were tiny, 0.0771 for ID and 0.0890 for ODE.
Okay, so one measure says medium effect, another says negligible. How does that work?
Yeah, it seems contradictory, right? You wonder if the improvement is really significant after all.
Yeah.
But the paper explains this apparent mismatch really well by introducing the concept of a bimodal distribution of accuracies. You can see it clearly in their figure 2. What this means basically is that for most tasks, the models either solve them perfectly 100% accuracy or they fail completely 0% accuracy. There's very little in between, very few partial successes.
Ah, because of the exact match grading.
Precisely. That exact match grading criterion we talked about off by 1 pixel, score is 0, no partial credit. So this bimodal pattern emerges directly from that. Most tasks are either totally right or totally wrong. Now, Cliff's Armin is a non-parametric measure of how much two distributions overlap, because most tasks are clustered at 0% or 100%, even shifting a noticeable number of tasks from the 0% cluster to the 100% cluster doesn't drastically change the overall overlap measured by Cliff's Arm. It remains small.
Okay, so the statistic is small because of the shape of the distribution, even if the mean shift is meaningful.
Exactly. So while Cliff's Arm might be small, the mean accuracy improvement for ODE tasks going from 31.08% for DARC up to 38.98% for DAMP still corresponds to an expected 7.90% increase in the number of grids solved entirely correctly for any given RA task. That isn't just a statistical blip. It means, practically speaking, DAMP is solving nearly an additional 8 out of every 100 ODE task instances perfectly that DARC simply cannot solve at all.
That sounds practically significant.
It is. And this improvement holds up statistically, too, as the 95% confidence intervals for the mean difference clearly exclude 0 for both ID and OID tasks. So the bottom line is that gains are statistically significant and practically meaningful, even though the bimodal distribution makes some effect size measures look small. The shift from unsolved to solved is real.
So let's loop back then to the central mystery here, because this is what makes the paper so compelling, I think. Given the incredible architectural similarity between DARC and DAMP, literally just one added component, that single MLP, and the fact that the 3x3 convolutions in DARC already do nonlinear channel mixing, why? Why did adding this one gated MLP have such a profound, such an outsized impact on performance, especially on generalization? It feels really counterintuitive at first glance. You'd think you'd need a much bigger architectural change for that kind of leap. What do you think is really going on under the hood?
That really is the million-dollar question, isn't it? And it's a point the paper itself flags as fundamentally surprising. Their conclusion is pretty clear. DAMP learns more complex mappings and generalizes better, especially ODE. The core surprising finding, as they put it, is that simply allocating additional compute to the processing of channels between convolutions allowed a surprisingly large performance boost in parameter-matched settings. This really begs for a deeper look. Yes, 3x3 convolutions mix channels non-linearly, but their mixing is inherently localized. It operates on a small neighborhood of pixels and their corresponding channel features right there.
Okay, local mixing versus something else.
Right. The added MLP, operating channel-wise, likely allows for a more global or maybe a more abstract form of channel mixing across all the features at a given location. Think of it maybe like this. A convolution might learn a simple rule like, if channel A has value X here and channel B has value Y nearby, then output Z. But the MLP might learn a higher order relationship across all channels at that point. Something like, if the overall pattern across channels A, B, C represents feature type 1, and the pattern across channels D, E, F represents feature type 2, then activate this specific combination.
Ah, so it's combining higher level features detected by the channels.
Potentially, yes. It might be learning to effectively weigh or combine the information content from different feature maps in a way that's much more flexible and maybe more robust than the fixed perceptive fields and simple mixing of convolutions alone. For instance, if one channel detects horizontal lines and another detects vertical lines, the MLP could learn a complex rule that says if there's a strong horizontal signal, A and D, a strong vertical signal here, this likely represents a corner concept. It's not just mixing raw pixel info, it's mixing learned features in a potentially more sophisticated way.
And the GLU gating helps there.
Absolutely. That GLU gating allows for selective information flow. It lets the network learn to focus on the most relevant combinations of channel information and suppress irrelevant ones for the task at hand. That's crucial for generalizing, especially when inputs might be noisy or varied. So the takeaway isn't just adding more nonlinearity randomly. It's adding it in a specific place between convolutions, operating channel-wise in a way that seems to foster more efficient and effective learning of these abstract, high-level feature interactions across the entire representation. That seems to lead to more resilient and transferable knowledge, which is key for ODE generalization.
Okay, stepping back now, the implications of these DAMP findings, they feel like they extend pretty far beyond just this specific RE-ARS benchmark, right? This work represents a really significant boost to the generalization abilities of these recurrent convolutional architectures, especially in those critical out-of-distribution scenarios we've been talking about. What this means, really, is that this research opens up what the paper calls a novel avenue for making real progress on the ARC challenge, and probably similar problems that demand strong generalization from very limited data.
Yeah, it's a new tool in the toolbox for tackling generalization.
We're talking about potentially building AIs that can truly understand and apply the underlying rules, not just memorize examples or interpolate within the data they were trained on. That feels like a vital step towards more flexible, more adaptive AI systems, ones that don't need retraining from scratch for every little variation in a task. Hashtag BB, addressing challenges in existing neural program synthesis approaches.
And a really key insight here is how DAMP's approach contrasts quite sharply with many of the current neural program synthesis methods that have been getting attention. Often, these other methods involve a neural network that tries to generate explicit, human-readable code, usually Python code, right?
Yeah.
Which is then executed to produce the final output grid.
Right, the network writes a program.
Exactly. And while that's conceptually appealing, it sounds like program synthesis, it actually runs into a couple of main problems, as this paper thoughtfully points out. First, not all RRC tasks actually have neat, discrete Python solutions. Some tasks seem to rely more on visual intuition or analogical reasoning or subtle pattern recognition. It's just really hard to capture formally in a symbolic programming language.
Like trying to write code for recognizing a style of art. Hard.
Exactly. Think of trying to draw a freehand sketch versus writing a precise mathematical formula for that curve. Some things are just hard to codify symbolically. Second, and this is perhaps even more critical from a machine learning viewpoint, Python programs, once they're generated, they are not differentiable.
Ah, okay. Can't backpropagate through the code.
Precisely. That's a major technical hurdle. It means those methods cannot directly benefit from test time training. This is a powerful technique, shown by Okurek and others in 2025 to be highly effective on ARC tasks. Test time training lets a model make small adjustments, refinements to its internal state, maybe even its weights, based only on the few shot examples provided at test time for that specific problem instance. It effectively learns to solve this specific instance better.
Fine-tuning on the fly for the current problem.
Right. But if your output is non-differentiable code, you can't easily backpropagate the error signal from the test examples all the way back to refine the neural network that generated the code. It breaks the chain of learning. This really limits the system's ability to fine-tune its approach for novel, unseen tasks. DAMP, being a neural network itself that directly produces the output grid, completely sidesteps this differentiability problem. It's end-to-end differentiable. ###C. The promise of hypernetworks and DAMP is a target architecture.
Okay, so if generating Python code directly has these limitations, especially around differentiability and test time tuning, what's the alternative approach to neural program synthesis that DAMP seems so well suited for?
This brings us to the really interesting concept of the hypernetwork. It's not a new idea overall, but applying it here seems particularly promising. A hypernetwork basically is a neural network that when you give it a few shot example or a problem description, it doesn't solve the task directly. Instead, it generates the weights, all the parameters, the internal settings for a separate target network. And it's that target network that then actually solves the task.
So one network generates the parameters for another network.
Exactly. And the profound advantage here is that this generated target network, once the hypernetwork spits out its weights, can be further tuned and refined using the provided examples, because it's just a regular neural network.
Ah, so the target network is differentiable. Right. This crucial step directly allows for test time training, completely bypassing that differentiability roadblock we just discussed with code generation. It's like having an AI that learns how to build another specialized AI for the task, and then that specialized AI can immediately learn and adapt from just a few examples.
That's a really powerful paradigm. But it raises an important question. What's the main challenge with this hypernetwork approach? Well, the biggest hurdle is finding a target architecture, the network, whose weights are being generated that strikes the right balance. It needs to be expressive enough to actually solve a wide variety of complex tasks, like the ones in ARC. And it needs to be small and efficient enough for a hypernetwork to realistically generate all its weights on the fly for every new task. You can't have a hypernetwork generating billions of parameters instantly.
Right. The target network needs to be capable, but also compact enough to be generated quickly.
Precisely. And this is exactly why the paper highlights DAMP as such a promising candidate to be that target architecture. It demonstrates really strong performance across 185 diverse rearc tasks using just a single fixed network configuration. That's powerful evidence for its inherent expressiveness and versatility. Plus, its recurrent nature already lets it handle variable-sized inputs, which is fundamental for RS, and it could likely be extended to handle tasks that don't preserve grid size, maybe through padding or other mechanisms.
So it ticks the boxes for a good target network, capable and flexible.
It seems to. And there's also strong precedent for hypernetworks working well in other domains. Volk and colleagues in 2023 showed hypernetworks are already effective for few-shot generation of classifier weights in MLP. So the idea of using a hypernetwork to generate dance weights specifically for ARS tasks, that seems like a really exciting avenue for future research, as the paper puts it. It marries this powerful learning paradigm, hypernetworks, with a highly capable and efficient target architecture.
Now, amidst all this excitement about DAMP and hypernetworks, it's absolutely crucial we insert an important clarification here. It's one the paper itself makes very clearly and honestly. This impressive demonstration of DAMP's capabilities, as significant as it is, does not mean we now have a general solution to ARS-AGI, that's artificial general intelligence in the context of ARC. It's really vital for listeners to understand this distinction to keep expectations grounded about what this breakthrough actually means for the bigger picture of AI.
Absolutely. The paper draws a very precise, very important line here. A true RC-AGI solution, by their definition and generally accepted understanding, would require few-shot generalization to completely new tasks. That means you could show the AI just a few examples of a totally new type of puzzle, a rule it has never encountered before in any form during training, and it would immediately grasp the underlying abstract principle and apply it correctly.
Learning truly novel concepts from scratch, basically.
Exactly. What this work does show, and shows powerfully, is strong out-of-distribution performance on a single task after extensive training on simpler versions of that same task. So, DAMP handles harder, more complex versions of tasks it has seen in simpler forms during training really well. But it's not yet making that leap to entirely novel problem types with only a handful of examples.
So it's generalizing within a task family, scaling complexity, but not yet generalizing across fundamentally different task families from few examples.
That's a great way to summarize it. It's generalizing task complexity, not necessarily task novelty from few shots. Nevertheless, this type of ode generalization, where complexity scales up significantly, provides really important evidence. It suggests that DAMP's inductive biases, the inherent assumptions and preferences the network has for learning certain kinds of patterns and relationships, are well aligned with the types of reasoning patterns needed for accuracy.
So it has the right kind of built-in structure or learning preference for these problems.
It seems that way. This is a strong foundational step. It shows DAMP has the right kind of intuition or structural propensity for these abstract problems, even if it's not yet learning entirely new ones completely on the fly from just two examples. It suggests DAMP is perhaps thinking in the right way for ARS problems, even if it still needs extensive exposure to the specific problem type first.
Okay, and just before we start to wrap up this deep dive, I wanted to quickly touch on some extra information they included in the appendix. It's about something called an optimizer ablations study. This is where they checked if their main findings were maybe just a lucky result of the specific optimization algorithm they used during training. It's a really critical step for checking how robust their claims are.
Yeah, it's a key piece of due diligence, and it adds confidence to the findings. The muon optimizer was chosen for the main experiments because their initial tests showed it clearly outperformed the more common baseline, AtomW, for both DARC and DAMP architectures on these tasks. So muon just seemed like a better fit for this particular problem and network type. Help both models perform better overall.
Okay, so muon was better for both.
Right. But the critical takeaway from the optimizer ablation study is that the distinct performance advantage that DAMP holds over DARC. It remains significant even when both architectures were trained using the less effective AtomW optimizer. For instance, even with AtomW, DAMP still beat DARC on ode tasks, achieving a mean accuracy of 9.04% compared to DARC's 5.28%.
So the gap was still there, even if the absolute numbers were lower.
Exactly. While the overall accuracies dropped for both models when using AtomW, that relative performance gap, DAMP being better than DARC, persisted clearly. And this confirms, pretty definitively, that the performance difference they observed between the two architectures is genuinely due to the architectural innovation in DAMP, that single, strategically placed MLP, and not just an artifact of picking a particularly good optimizer. It really reinforces the robustness and the fundamental nature of their findings. It suggests DAMP's superior generalization capability is an inherent property of its design, not just a side effect of the training setup. It's strong validation that the MLP itself is truly doing something impactful.
Good to know the core finding holds up regardless of the optimizer choice. Hashtag Paul outro. So what does this all really mean for the broader landscape of AI? Our deep dive today, I think, has uncovered something genuinely exciting. We've seen how a seemingly simple yet incredibly precise architectural tweak, just adding that channel-wise MLP inside the loop, can dramatically boost the generalization capabilities of these recurrent convolutional networks. And this boost is especially pronounced when these networks face those really tough, unseen, out-of-distribution problems, the kinds of problems that truly test an AI's capacity for abstract reasoning, pushing it way beyond simple pattern recognition.
Yeah, and if we connect this back to the bigger picture, these findings really do open up some exciting new possibilities, particularly for neural program synthesis. They firmly establish DAMP as a very promising candidate architecture, maybe as a target for those powerful hypernetwork approaches we discussed. That could be a key pathway towards creating more adaptable, more generalizable AI systems that learn how to learn more effectively. It's a really compelling evidence, I think, that sometimes small, precise architectural changes, when they're strategically applied, can unlock quite significant advancements in how our AI models understand and adapt to the world. It pushes them a little closer to that human-like abstract reasoning ability.
It feels like it's about finding the right computational primitives, the right structures, not just throwing more layers or parameters at the problem.
Well, exactly. Quantity of computation, perhaps.
Okay, and that leaves us with a final provocative thought for you, our listeners, to mull over as you go about your day. If such a minimal yet clearly targeted architectural change, like adding this MLP, can yield these striking results in generalization, what other subtle structural innovations might be waiting out there, undiscovered within neural networks? What other small, precise tweaks, maybe in how information flows or how different computational units interact, could unlock even greater leaps in AI's ability to reason abstractly and generalize to truly novel problems?
How do we find those fundamental computational patterns?
Exactly. How will we discover these fundamental patterns that can help bridge that massive gap from training on relatively simple examples to solving entirely new and complex challenges? Something to think about. Thank you for joining us on this deep dive.